hydrogen nuclei fuse together to form helium nuclei in the Sun. Two stages in the process are represented by the following equations. Part 1, describe the reactions that these equations represent. And Part 2 is calculate the energy released in each reaction, where the masses of the various particles, so a beta plus, a proton, hydrogen 2, and a helium 3 nucleus are provided. So, 3b, let's look at part 1 initially. And what we've actually got then is a reaction that's involving two protons. So we've got a proton and another proton. And that goes across and it tells us that gives us a hydrogen 2, or deuterium, plus a positron. Now the reality is actually it would also give us an electron neutrino plus energy actually emitted out of there as well. Now it wants us to describe the reactions in this process. So if we look at it, then what's going to happen is we've got the fusion of two protons to make, or to form, hydrogen 2, or to form a hydrogen 2, which is also deuterium nucleus, releasing a positron, an electron neutrino, and some energy. Okay, so from that perspective, if I put R in energy, so from that perspective we've got that reaction, we described what's actually going on. So the second part is then, the second equation we're actually given is we've got a deuterium, I assume nucleus, plus a proton is going to give us helium 3. So in this case what's happening is fusion of a hydrogen 2 nucleus, which we could also call deuterium, and a proton, to give a helium 3 nucleus, HEUS, and releasing energy, because this fusion as well would actually release some energy, so you've got some plus energy actually released as well. 1 done. We're going to look at part 2. Now part 2 then, it's asking us to do the calculations in terms of energy, and it's giving us the reaction masses of each of the components. So if we actually work through it, the first one we're going to look at then is proton plus a proton, which is reacting to give us deuterium plus a beta plus particle. An anti-electron neutrino we're going to ignore, and obviously it's going to give us some energy actually came out as well. So the rest mass of this side then is 2 times by, now the rest mass it gives us of a proton is 1.00728U. This then we've got a deuterium, it tells us that nucleus has got a rest mass of 2.01355U. It tells us the beta particle's got a rest mass of 0.0005U. So this ends up with this plus some energy. So to work out how much energy is actually released, we're going to work out the mass defect. And that's going to be the mass before minus the mass after. Because that, whatever that defect is, that additional mass is going to be have lost as energy. So what I've got then is I've got 2 times by 1.00728U minus 2.01355U minus 0.0005U. And that gives me a mass defect of 2 times 1.00728 minus 2.01355 and minus 0.000055 it should be, gives me a mass defect of 4.6 times 10 to the minus 4U. Now, earlier in the question, it tells us that 1 U equates to 931 mega electron volts. So therefore, my mass defect is that many U, which means it's 4.6 times 10 to the minus 4 times by 931 mega electron volts. So times that by 931 gives us 0.42826 mega electron volts. Now, if I have a look through this, these are all 1, 2, 3, 4, 5, 6 significant figures. I guess you might argue that's only 2 significant figures. So on that basis, I'm going to go for 2 significant figures. So that means I'm going to get 0.43 mega electron volts to 2 significant figures. That's my least precise answer. So that's the first bit. The second reaction then, what I've got is deuterium. So I've got hydrogen 2 plus a proton is going to give me a helium 3 nucleus plus some form of energy out. So if we look at these, hydrogen 2 nucleus has a mass of 2.01355U. The proton's got a mass of 1.00728U, and that gives us a helium 3 nucleus, which has got a mass of 3.01493U. So same idea as before. We've got to work out the mass defect. So the mass defect again is the mass before minus the mass after, which tells us how much mass was lost and therefore how much energy is released. So the mass before is 2.01355U plus 1.00728U. Mass after is, that was a point there, 3.01493U, giving us a mass defect of 2.01355, delete 01355, minus 1.00728, oops, that's wrong, plus 1.00728, minus 3.01493, gives us a mass defect of 5.9 times 10 to the minus 3 U. So it's positive, so mass has been lost, therefore energy has been released. Again, 5.9 times 10 to the minus 3. Each U, it told us before, was 931 mega electron volts, so that's times by 931 is going to give us 5.4929 mega electron volts. Now if I look at this then, everything here, I think I've got 3 significant figures is my worst, so therefore I'm going to go 5.49 mega electron volts to 3 significant figures for this one. Hopefully that makes sense. Thank you very much.